Hey boys and girls, welcome to day 4 of calculus. And today I'm so excited. I get to actually introduce you to your first calculus lesson. Are you excited? I'm excited. These notes can be found on pages 8 and 9 in your guided notes. So I invite you to follow along. A lot of the things are already written for you so that you don't have to do a lot of writing. You can just kind of fill in the blanks and absorb what's being said here. So this first lesson will be broken up into 2 videos. In this first video, our objective is going to be to find the value of a limit, and we're going to do that 3 different ways. We're going to find the value of a limit numerically, algebraically, and graphically. In this class, you will always be asked to represent things in multiple ways. So you'll see that we will always, well, not always, but we try to do things algebraically, verbally, and then also tabularly. All of those different ways you will be asked to explain your knowledge. So in this lesson, the 3 ways we're going to explain our knowledge is algebraically, numerically, graphically. This is the informal definition of a limit. This is found at the top of page 8 in your notes. If you don't want to have to write all this down, it's already there for you. So basically what a limit says, if you have the y value of an x, of f of x, the y value, as x gets closer and closer to some number, if that y value gets closer and closer to that number from both the left side and the right side, then the limit exists. Now, according to this definition of limits, a limit must be a finite number. There's some dispute about that in the math community. Some talk about that a limit could say that it's infinity, but in this class we're going to say that a limit exists if it approaches a finite value from both the left and from the right. Please note the limit notation. The limit as x approaches c. X is that x value that is approaching, and f of x is the y value that corresponds to that x value. So we're going to start by finding the limit numerically. I want to give you an example. We're looking for the limit as sine x over x and the limit as x approaches 0. Now, just from a quick look at this function, we notice that if we just were to put 0 into the function, we get sine 0 over 0. What is sine 0 over 0? It's 0 over 0. We know from experience that we can't divide by 0. And actually that form 0 over 0, we're going to call that indeterminate. And we're going to talk about that later in the video, but that's called an indeterminate form when you get 0 over 0. So let's look at it numerically. If I were to use my handy dandy calculator and I would put some values in for sine x over x as x approaches 0, I'd get a table that looks sort of like this. Notice I started by putting in numbers to the left of 0, negative 0.1, negative 0.01, negative 0.001. Those numbers were getting closer and closer and closer to 0. Then from the right, I started by putting a number like 0.1, 0.01, 0.001. Those numbers getting closer to 0. And what did I notice about my f of x values? My f of x values got closer and closer to 1. I'm using this new table, so please bear with me. And so we can say that sine x over x, the limit as x approaches 0 of sine x over x is 1. Now what I want you to notice, I want you to memorize this because this comes up later. But what happened was as we got closer and closer to 0, our x values got closer and closer to 0, our y values got closer and closer to 1. Now this is actually an approximate value because our calculating could not estimate any to more decimal places. But we would see that this never actually approached 1, but it just got closer and closer to 1. But this is what our calculator showed us. Let's do another example. So let's say we have 1 over cosine x over x. Again, if we just put in 0, we would get 1 minus 1, which is 0, over 0. And again, 0 over 0, we're going to call that indeterminate. We can't do it. It's indeterminate. So again, taking a table of values, notice that I started at negative 0.1, and I got closer and closer to 0. On the other side, I started at 0.1, again, getting closer and closer to 0. And I noticed that my values are getting closer and closer to, actually it's getting closer and closer to 0. My y values are getting smaller and smaller and smaller. And if I were to keep going making those x values smaller and smaller and smaller, I would see that I am getting closer to 0. So we say the limit as x approaches 0 of 1 minus cosine x over x is also 0. So this, I wanted to show you this to show you how this works numerically. Now, I would never ask you to do a problem like this without a calculator, or if I gave you a problem like this, I would give you the table and ask you to find that value numerically. So I need you to remember these limits. These are going to come back. These are going to be important when we get to the second video. So just memorize these limits. I don't have a place for you. Well, you should have written the answers down here. Notice that the limit as x approaches sine x over x, because it's just the converse of this, is the exact same thing. It's they're reciprocals. So it's the same thing. Okay? Okay, boys and girls, now we want to look at finding limits graphically. And so there's a couple of things I need to remind you of before we go there, just to make sure we're on the same page. So for instance, when we see an open circle like we see here, that open circle means that it is not, that function does not exist at that point. So we can see that this function exists at x equals 3. It exists at 1 because that's where it has a closed circle. So the function does not exist at when x is 3 and y is negative 2. The function does not exist at that point because there's an open circle. Another thing I think I need to probably remind you of is some notation. So in this first problem, we notice as x approaches 3 from the left. So I want to remind you that when you have the limit as x approaches 3 and this negative sign, that means from the left. And when you have the limit as x approaches 3 and that plus sign, that means from the right. Okay? So you just need to be aware of that notation. So in this first question, it asks the limit as x approaches 3 from the left, because there's just that small little negative sign. So that means from the left. So what I'm going to do is I'm going to trace the line starting from the left of the graph, and I'm approaching x equals 3. As I get closer and closer to x equals 3, y gets closer and closer to what value? Y gets closer and closer to 1, 2, 3. 1, 2, 3. Y gets closer to 3. So then we can say that the limit as x approaches 3 from the left is 1, 2, 3. It is 3. Okay, so the answer to this first one is 3. Wrong pen, sorry. I haven't used this tablet in a while, so please bear with me. So that's equal to 3. Then when we have the limit as x approaches from the right, we're going to trace this. Starting from the right, we're coming into the graph, and we see that it's approaching which number? Negative 2. So we negative 2. So the limit as I approach x from the left of 3 is 3. The limit as I approaches x from the right of 3 is negative 2. So therefore, since the left-hand limit does not equal to the right-hand limit, the limit as x approaches 3 does not exist. This last question asks, what is f of 3? Well, f of 3 would be this value. Okay, so the limit as we approach from the left is 3. The limit as we approach from the right is negative 2. F of 3 is 1, but the limit itself does not exist because the left-hand limit does not equal to the right-hand limit. Okay, boys and girls, what I'd like for you to do is I'd like for you to pause the video, and I would like for you to try these 4 problems on your own. Okay, welcome back. Let's see what happens. So the first one asks us to find the limit as x approaches 2 from the left. We're approaching 2 from the left. So what I'm going to do is I'm going to come down, and I'm coming from 2 from the left, and as that happens, the y value is getting closer and closer to 1. Even though it does not exist at x equals 2 and y equals 1, my y values are still getting arbitrarily closer and closer to 1. So I would say my answer for that part would be 1. Okay, the second one says find the limit as x approaches 2 from the right. So now I'm going to approach 2 from the right, and I see that as I come in from the right, my y value is still getting closer and closer and closer to 1. So therefore, what is the limit as x approaches 2? So the limit from the left is 1, the limit from the right is 1. Therefore, the limit as x approaches 2 is 1 because my left-hand limit and my right-hand limit are the same. But notice g of 2 is 1, 2, 3. G of 2 is 3. So what does that tell me? That tells me that I can have a limit even though the function doesn't exist at that point. The limit could still exist. Even though the function does not exist at 2, 1, the limit exists. Okay? If you would go to the bottom of page 8, there's a little box and some graphs. I want you to take a moment, pause the video, and I want you to complete that box and come back in a few minutes and I'll give you the answers. Okay, boys and girls, welcome back. Here's the answers to those problems. If you have any questions on any of these, please make sure you mark it and then be sure to ask me tomorrow when we have our time together. Okay? Okay, boys and girls, on this slide, we're looking at the limits of a piecewise function. Notice that piecewise functions are broken into pieces. So when we're determining if we're looking at a value from the left or from the right, we have to determine which piece of the piecewise function is applicable. To help us see that, I have taken the liberty of simply just graphing this piecewise function. So notice in this first question where we're asking for the limit as x approaches negative 1 from the left, what we're looking at is this piece of the graph. And we can see that as it comes to negative 1, it's going towards 3. But we could also determine that if we would simply evaluate this part of the expression, because it says x is less than negative 1, therefore that means it's coming in from the left on this piece of the function. So I would simply do a direct substitution into the problem, and I would get 2 minus negative 1 equals 3. Okay. So when we're looking at x approaching the graph from the right, now we want to look at the part of the function where it's coming in from the right. So we see that this is coming in from the right and it's going to approach this value. And what is that value? To find that value, we would evaluate this part of the function. So just doing a direct substitution, we're going to get f of x is equal to -1. Now, what I want you to notice, even in this first part, it's not defined at -1. The top piece of this function is not defined at -1. If I were to draw that, it would have an open circle. But remember, we're looking at the fact that it's getting arbitrarily close. So it's getting arbitrarily close to 3 here. Here, it is not just getting arbitrarily close to -1. It is actually -1 at that point because it's less than or equal to. So what does that mean? Does the limit as x approaches -1 exist? And the answer to that would be it does not exist. And why doesn't it exist? Because the left-hand limit is not equal to the right-hand limit. Okay? What I want you to do is I would like for you to pause the video and try the last line, and then we'll come back and talk about it. Okay, welcome back. So when we're looking at the limit as x approaches +1 from the left, once again, we're going to look at this middle, let me get a different color, highlighter here. We're going to look at the middle part of this graph. So if I look at the graph, what I see is that I am coming from the left to 1. And I see that even though there's an open circle there, it doesn't exist. That value is still 1. And again, what I did was I evaluated this using this middle piece. So I used that middle piece to evaluate that. When I approach f of x of 1 from the right, I'm going to use the bottom piece of that function. And that's going to give me, looks like 0. Because I'm coming in, but I'm also using this bottom function as well. So if I do a direct substitution, trying to get a pen again. If I do a direct substitution, I get 1 minus 1 squared, which is 0. Okay? So once again, does the limit exist? No, the limit does not exist because the left-hand limit does not equal to the right-hand limit. So it does not exist because the left-hand limit does not equal to the right-hand limit. Equation. Okay, now boys and girls, we're going to move to my favorite part of this discussion, and that is evaluating the limit algebraically. In this section, we're going to use 3 different methods to evaluate a limit algebraically. The first method we always start with direct substitution. We try that before we try anything else. With direct substitution, we do it because it's just quick and dirty. So direct substitution is simply just replacing the x value with the value that the limit is approaching. And we saw that when we were evaluating piecewise function. If direct substitution doesn't work, and it doesn't work when the limit is indeterminate. So if you get a 0 over 0 or infinity over infinity, in calculus we call that indeterminate. And so if you try direct substitution and you get 0 over 0 or infinity over infinity, you're going to have to use a different method. Today, the 2 methods you're going to use are simplifying and rationalizing the numerator and denominator. Simplifying could be factoring. It could be finding the least common denominator of a rational function. It could be using some of your trig identities that we learned early in the week to manipulate the function. You can also try rationalizing the numerator or denominator. Now, I know in classes past, they've drilled in your head rationalizing the denominator, but in this class, we sometimes find it necessary to rationalize the numerator. So you need to be familiar with conjugates as well. Okay, boys and girls, we're on page 9 of your notes, and we are on the very first problem, which asks us to find the limit as x approaches 3 of radical x plus 1 over x minus 4. Well, according to our notes from the previous slide, our first step is always going to be to try direct substitution. So again, direct substitution is just substituting in wherever x is going to. So in this case, as x approaches 3, we want to substitute all of our x values with 3. So what does that look like? That's simply going to be the square root of 3 plus 1 over 3 minus 4. And because I'm actually substituting in, I did not write the limit because I'm actually doing the substitution. So that'll give us the square root of 4 over the square root of -1. So our answer is -2. And that is a simple direct substitution. Easy peasy. All right, let's try the next one. Now, when we try to do a direct substitution for this one, we get the limit as x approaches -1 of x plus 3 would equal to -1 plus 1 is equal to 0. Then we get the limit as x approaches -1 of x plus 1, the denominator, and that's equal to 0. So that would give us indeterminate 0 over 0. Now, College Board, indeterminate. College Board does not like it when we write 0 over 0. So we don't write that. We just say that it's indeterminate. It doesn't like it, so do not write it. If they will take off, I will take off. Do not write 0 over 0. So we just say that that's indeterminate. So what are we going to do to solve this problem? So let's try, I don't know, anybody have any suggestions? How about factoring? So we have to recall, and I hope you remember this from Math 3, we're going to take the factor of the sum of 2 cubes. If you do not remember that, please Google the sum of 2 cubes to get the formula. And if after Googling you still don't understand, you can come see me. So you can't come see me, but you can ask that question tomorrow in synchronous learning. So to factor, so I'm going to keep saying the limit because I'm still taking the limit. To factor that, I get x plus 1. Then it's going to be x squared minus x plus 1 all over x plus 1 remains the same. Okay, so we know from algebra that those two cancel out, and so I am left with the limit as x approaches -1 of x squared minus x plus 1. Notice that my notation that I am writing the limit. I continue writing the limit until I actually do the direct substitution. So the limit of this would be -1 squared minus -1 plus 1 all, well, there was nothing there, so there's not anything, over 1, I guess. So what is that? That's 1 plus 1 plus 1 is 3. Okay, and that is our answer using direct substitution. Now I could write the limit here because notice here I said the limit as x approaches -1 is equal to, and then I just did a direct substitution. But you do want to be careful how you write an equal sign and make sure the two things you're writing are in fact equal. Okay, boys and girls, this problem is beautiful. It has all kinds of wonderful things in it. It has radicals, and it's just beautiful. So let's try this. The first thing we want to do is a direct substitution. So substituting in 0 for x, I end up with radical 2 minus radical 2, which is 0, and then 0. So I get 0 over 0, so it's indeterminate. So what should I do? Well, the radicals are going to tell me that I should probably multiply by a conjugate or rationalize the numerator. In this case, we're rationalizing the numerator. And to do that, we're going to multiply by the conjugate. And so the conjugate here is the same as what we have in the numerator, except for the term of the second term changes. The second term sign changes. So instead of being -2, it's going to be +2. Now, as a general rule, when I were to multiply this out, I would probably just use the shortcut in my head to do it. But since we haven't done this before together, I'm going to just multiply it out the long way, show you the shortcut, and never do this long way again. Okay, so we're going to use full to multiply this. So we're going to have the limit as x approaches 0 of, so to use full, I'm going to do radical 2 plus x times radical 2 plus x. So I'm multiplying the first terms of each. First, outside, so I'm going to multiply the outside terms, which are going to give me radical 2 plus x times radical 2, because I'm multiplying these two together. And then inside would be these two together. So that would be minus radical 2 times radical 2 plus x. And then last would be minus radical 2 times radical 2. So that would be minus, sorry, I keep running out of space here. That would be minus radical 2, radical 2. Okay, all over, we multiply the denominator, and we're not going to multiply that out. We're just going to leave it like it is. All over x parenthesis 2 plus x plus 2, close parenthesis. All right, now I know this looks crazy and ugly, but we're going to see a couple of things here. The first thing, the nice part about multiplying by a conjugate is that it eliminates the radicals. That's its whole purpose. So knowing what we know about radicals, when I multiply radical 2 plus x times radical 2 plus x, the radicals go away and I'm left with 2 plus x. When I multiply radical 2 times negative radical 2 times 2 plus x, and this one should be positive actually. That should be a positive. When I multiply positive radical 2 times 2 plus x minus radical 2 times 2 plus x, these zero each other out because one's positive and one's negative, so that zero each other out, so that's gone, and I am left with negative radical 2 times radical 2, which is just minus 2. So what do we learn from this? When we multiply by the conjugates, all we have to do is multiply these two together and then these two together, because the middles are going to cancel each other out. That's the beautiful thing about a conjugate. And it gets rid of the square root. It gets rid of the radical. So this would be 2 plus x, then plus radical 2. And all of that needs to be in parentheses because we're multiplying that quantity. So again, I'm still writing the limit because I have not taken the limit. So this is the limit as x approaches 0. 2 plus x minus 2 is just x. My denominator, I have not done anything to that, so it remains the same. Okay, now, if I do a direct substitution, I get 0 over 0 again. Bummer. But look at this. I can now factor. And when I factor, the x's cancel out. So now I have, again, I'm still writing the limit because I have not taken the limit yet, of 1 over square root of 2 plus x plus square root of 2. Now I can just do a direct substitution. When I do a direct substitution, I will no longer write the 0 and I will no longer write the limit. I will replace x with 0 and I get 1 over, I get something somewhere right here. I get 1 over the square root of 2. The x went away because it was the limit as x approaches 0 over square root of 2, which is equal to 1 over 2 root 2. Is that not fun or what? And that is our final answer. Okay, boys and girls, we have another problem here. What I want you to see for this problem is that delta x that you see, we treat that just as if it's a variable. So this delta x does not mean triangle times x. No, that is just a symbol, and it means delta x. It means to change in x. And you see this often in math and in science. So this simply is just delta x. We're going to treat it just like it's a variable. So in this first problem, when we do a direct substitution, if I put in 0 for delta x, I get x squared minus x squared, which is 0 over 0, indeterminate. So therefore, I'm going to have to use algebraic manipulation. So we're going to start by simply just simplifying this expression. So if I were to simplify this expression, I would start with the limit as delta x, because I'm not taking the limit just yet, I'm just simplifying. And I'm going to use 4 to multiply that out, and I'm going to get x squared plus 2x delta x plus delta x quantity squared minus x squared all over delta x. Now, if you have a problem with me multiplying that so quickly in my head, again, you can ask that tomorrow during class. Okay, so when I simplify this, I have x squared and I have minus x squared. So I see that those two zero out. And again, I haven't taken the limit. I'm still simplifying. I get limit as delta x approaches 0 of 2x delta x plus delta x quantity squared over delta x. Okay, if I try to do a direct substitution and for delta x is 0, I get 0 here, and 0 at the bottom, so I get 0 over 0. So what can I do? I have to use some algebraic manipulation. So therefore, we're going to factor out a delta x. So we factor out delta x, and we're left with 2x plus delta x all over delta x. Now, what did that give us? Well, now my delta x's, this delta x and that delta x cancels out. And so now I have the limit as delta x approaches 0 of 2x plus delta x. When I take that limit out to do a direct substitution for delta x, it goes to 0. So then I am simply left with 2x. And that is my answer. Okay, on this problem, we're going to have to well, first of all, let's do a direct substitution. So we do a direct substitution, we get 1/3 minus 1/3, which is 0, 0 over 0, indeterminate. So we're going to have to not rationalize, we're going to have to, it's a rational expression, we're going to have to find a least common denominator. Now, I might do that a little differently than you, but it's okay. We should end up in the same place, but you do whatever you need to do to add 1 plus 3 over x minus 1/3. Because when I add that together, what I get is 3 minus 3 plus x over 3 times 3 plus x all over x. And I'm still taking the limit. Okay? Now, however you got that, I'm just basically finding the least common denominator. Now I'm going to simplify that. And again, as long as I haven't done a direct substitution, I still have to write the limit. So the limit as x approaches 0, 3 minus 3 is 0. And I have to distribute that negative x, so that's going to leave me negative x over 3 and 3 plus x. And if you recall, remember I can write this as x over 1, so I'm going to multiply by the reciprocal. When you divide, you multiply by the reciprocal, so this is going to be times 1 over x. If I try to do a direct substitution, I get 0 over 0. So let me simplify. The x's will cancel each other out, and I'm left with the limit as x approaches 0 of negative 1 over 3 times 3 plus x. Now I can just do a direct substitution because x is 0. And so now that x is 0, when I do my direct substitution, this just becomes negative 1 over 3 times 3, which is 9. And that is my answer. And this last one, again, if I do a direct substitution, I do not get, because I wrote it wrong. This should be the limit as x approaches 3. Should be 3. All right, if I do a direct substitution, I get 0 at the numerator. At the bottom, I get 9 minus 12 plus 3, which is also 0, so it's indeterminate. So what can I do? Well, let's just do a basic factoring. So I have the limit as x approaches 3 of x minus 3 over factoring that. What can I multiply to get 3? Add to get negative 4, x minus 3, x minus 1. My x minus 3 is canceled. They make a whole. Well, we're going to call that removable discontinuity. So we have the limit as x approaches 3 of 1 over x minus 1. And just doing a direct substitution, we get 1/2. Okay, that's it, boys and girls, for this first. So what you want to do right now is to watch the second video on this lesson on properties of limits.